Hello everybody. Today we're going to learn about exponent rules. So this first video, it will just be a review about the rules, and then we'll get into some more examples. Of course, I'll use some little examples in this video. So the first rule is called the product rule. So if you don't know, product just means multiplication. So to multiply. So here, whenever you see this multiplication symbol, when you're multiplying two terms with the same base, you add the exponents. Of course, when you see variables, it's a little harder to understand what's going on. But let's say that we have an example and we have 2 to the power of 3 times 2 to the power of 4. Well, both of these problems have the same base. So we know it's 2. And then we add the exponents, which is 3 plus 4, which is 2 to the power of 7. So that is our first example. Another example will be 3 to the power of 2 times 2 to the power of 3. In this example, you'll notice that the bases are not the same. And since the bases are not the same, we cannot do the exponent rule, aka we cannot do the product rule. So for this problem, we'll just have to evaluate each one separately. 3 squared is 9, and 2 cubed is 8, and then we get the answer 72. So the rule of thumb here is don't force it. Another example, this time we're going to have 2x cubed times 5x to the power of negative 2. Here, as we can see in the front, we have the coefficient 2 and 5. 2 and 5 both do not have exponents here, so technically they have exponent of 1, and they're just regular numbers. So 2 times 5, we already know that this is just 10. No exponent rules were needed here. However, the x cubed, so this, and the x to the power of negative 2, we can use exponents rules here. They both have a base of x, and we can do 3 plus negative 2, which is just x to the power of 1, which is just 10x. So these are your typical examples of the product rule. The next rule that we're going to move in on to is called the power rule. So let's say that we have 2 to the power of 2 to the power of 3. The rule here is we just multiply and we get 2 to the 6. So once again, if you remember the rules, it's really not too bad to follow. But some of us might ask the question, why? So if we think about this, what we're doing here is we're taking what's inside, which is 2 squared, and we're going to multiply it 3 times. So technically it means 2 squared times 2 squared times 2 squared, or 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the 6. You always have the option to do it this longer way, but when you keep doing this over and over again, you just notice that the amount of times that you're multiplying the base just comes from multiplying the exponent or the power. That's why it's called the power exponent rule. So that's kind of like the background behind why that works. So that was an example. Let's try another example, which is our classic like 2x cubed y to the power of negative 2 to the power of, let's not pick 2, let's pick 4. So what a lot of people forget is that this 2 has a power of 1. If you can imagine what's going on here, you're taking everything into parentheses and you're doing it 4 times. But instead of writing it 4 times, we can just check this 4 and multiply each of our exponents. The thing about the coefficient in front is I'm never going to write 2 to the power of 1. That's something that you're going to have to write there and to remember that that's what's going on. So here we have 2 to the power of 4, x to the power of 12, and y to the power of negative 8. To get a sneak peek of the rule, remember that we usually do not like negative exponents, and we will have to take that and move it to the bottom. So 2 to the power of 4 is 16, x to the 12, and then we'll move y to the power of negative 8 to the denominator, which is y to the 8th. We'll talk more about that when we get to that rule, but that would be your final answer for that. The next rule is called the quotient rule or division rule. So if we have 2 to the power of 5 divided by 2 to the power of 3, we would just subtract the powers, and we get 2 to the power of 2, which equals 4. Or we can do 2 times 2 times 2 times 2 times 2 over 2 times 2 times 2, and divide out the 2's to get it 4. So remember, it's always better if we can do it the simplest, quickest way, which is that's why that we have this quotient rule to save time. So as an example, let's do another example, which might be 20x to the fifth, y to the third, 4x, y to the second. So remember here, it's kind of similar to the product rule earlier. When you have regular numbers and you're doing 20 divided by 4, we know this is a 5. And this is not an exponent rule. This is something that we already know how to do. When I see this x and then denominator, and I'm going to give it an exponent of 1, just to remind myself that we have 1x, and the rule is we subtract 5 and 1, and we get x to the fourth, and then we take 3 and 2 from the y's, and we subtract them, and we get a 1. And that's it for the quotient rule. The next rule, which is the strangest rule, is the zero exponent rule, which states that anything to the power of 0 is just 1. And the reason that we made this conclusion, the reason that we justified this before, was we took the question like 6 divided by 6. We know this is 1. Or 6 to the power of 1 divided by 6 to the power of 1. And if we use the quotient rule, it says that we subtract the powers and we get 6 to the power of 0. We know from here that 6 divided by 6 is for sure 1. And we know here that this is equivalent to this. So if everything in yellow is equivalent, then we know that anything to the power of 0 has to be 1. So if we do an example like this, 5x to the power of 0, we know this is 1 because if we wanted to, we could put a 1 here, a 1 here. We can write 5 to the power of 0, x to the power of 0, and we know this would be 1 times 1, which equals 1. Or if we have 5x to the power of 0, we see that this is different. Because what this means right here is this means 5 times x to the power of 0. As you can see, this answer is going to be 1. I don't know if or is really the best word. I don't think I meant that there. I just meant like these two problems look similar, but they're actually different because of the way that we are using the parentheses. So please keep this in mind while you do these questions. It's always about catching the little mistakes and little misconceptions. So next, we have the negative exponent rule. The negative exponent rule states that if we have 2 to the power of negative 3, that this negative 3 is telling me to do the reciprocal of this. So if I have this over 1, because I can always write the 1, I'm going to flip it and change that negative exponent to a positive exponent, and I get 1/8. Another example where this can be used is having it the other way. So let's use a variable. So in this case, the negative exponent happens to be in the denominator. So if we do the reciprocal, it becomes positive and it's over 1. But anything divided by 1 is just going to be itself. So we get y to the fifth. And now we have another example where we have only a certain base with the negative exponent. So when we see this problem, this negative 2 only applies to the y. So that means I'm going to keep everything just the way it is and just move that part to the denominator. And let's do an extra one, which is something like 5x to the fourth, y to the third, to the power of negative 1. As you can see here, I could technically multiply each of these by negative 1 if I want. But I can also think of all of this over 1 and just flipping the whole thing and changing that negative exponent to a positive 1, which would just be 5x to the 4th, y to the 3rd. Because by taking it to the power of 1, it doesn't change anything. So there's different ways to look at that. If this part confused you a little bit, I would kind of slow down, rewind, and kind of see like why this works. Like if you did this the longer way, this would be 5 to the power negative 1, x to the power negative 4, and y to the power negative 3. We know that we could put all this over 1, and if we did the reciprocal, that we would get the same result as we did here. So once again, like, make sure that you're understanding what you're doing and you're asking questions about what is happening. The next part is when we have a rational exponent. So I think the best way to kind of introduce this is like using this example, 9 to the power of a half. So 9 to the power of a half pretty much means that I'm going to copy this notation here. So my base is 9, my root is 2, and my power is 1. So the square root, this tells you, or this asks you, what same two numbers multiply to give you 9. So what same two numbers multiply to give me 9? Well, that's 3. And 3 to the power of 1 is 3. So 9 to the power of a half is saying the same thing as the square root of 9. Notice this time that I did not write anything where the root is. It's because we use the square root so many times that we just don't write 2. It's just known that a 2 is there. So let's do an example where that is not true. So like 8 to the power of 2/3. So I'm going to write my 8, my 3, and then I'm going to square it. So when I do this time is a 3. So I'm asking what same three numbers multiply to give me 8. Well, the answer to that is 2, and then 2 squared, which is 4. So 8 to the power of 2/3 just gives me 4. So what do I do now if I just give you a variable as a base and you have a rational exponent? Well, you just do x, 4 to the power of 5, or what I didn't write was that this is equivalent to this. So having this out here and having this in here will give you the same result. The reason why I normally do not use this like form over here is because I do not want to have a bigger number inside the radicand because I just want the math to be simple. Like I like the cube root of 8 instead of taking the cube root of 64. So those are just some little things to keep in mind. And besides that, you treat all these fractions just the same way as you do numbers. So let's say that you had like something like this. And let's say this is to the power of 3/4. First thing I learned is I'm going to give a 1 to the 16. I'm just going to go ahead and I'm going to multiply these just because I can. I'm going to have 16 to the 3/4 x, 2 times 3/4 y, negative a half times 3/4. I'm writing these down just to show you how to do the math because sometimes I feel like we forget how to multiply fractions. So technically this is over 1. So what is 16 to the 3/4? Honestly, I don't know just looking at it. So I'm going to rewrite it in radical form because now this is something I could do. 4 through to 16, or what same number do I multiply 4 times to give me 16, is 2. And I get 2 cubed, which is 8. So I know by doing that yellow part that I'm going to get 8. How do I multiply fractions up here? Well, I just multiply across. So I'm going to get 8x to the power of 6 over 4. I'm going to get y, multiply these two, multiply across, and get negative 3 over 8. I know that I can take this part and I can move it to the denominator because of that negative exponent. I know I can take 6/4 and I can simplify that to 3 over 2 since they're both divisible by 2. So I get 8x to the power of 3 over 2 over y to the power of 3/8. And this is my final answer. And this is the end to my video. Once again, I really didn't do a lot of crazy examples here. The big thing is, can I understand the rules and be able to start a problem, look at it, and examine it and see if you can make a move and follow through. I hope this video helped.